This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Global infrastructure grids and logistics networks are hitting a computational ceiling. When scheduled tasks reach a certain density, the resulting combinatorial load overwhelms legacy processing systems. The hardware fails to calculate the optimal path. The response to this bottleneck is the Quantum Kernel Co-processor, or QKC, a software-defined framework that transforms complex domain problems into accelerator-ready instructions. The operational doctrine is straightforward. Deploy these software-defined coprocessors on existing infrastructure today and prepare the environment for sovereign quantum hardware later. The system separates the mathematics of a problem from the physical machine running it. You structure the problem once, and the architecture executes it across whatever classical or hybrid processor is currently available. This completely removes the risk of vendor lock-in. Institutions secure an immediate increase in operational capacity using current processors. When physical quantum hardware finally matures, the existing software stack remains intact. This diagram shows the 8 distinct layers of the QKC architecture. Raw domain problems enter at the base and move up into the central translation layer, known as the intermediate representation, or IR. It acts as a portable translator, formatting problem structures so they can be processed by any admissible hardware backend. Instead of rewriting code for every new chip, the IR takes the standardized institutional problem and outputs instructions tuned for multiple execution targets, whether they are GPUs, HPC clusters, or quantum simulators. Above the IR, the runtime layer takes over. It assesses the available hardware, checks the active governance constraints, and automatically selects the optimal path for that specific workload. It removes user guesswork from the execution pipeline. By locking the problem logic inside the portable IR layer, the workload is completely isolated from the hardware beneath it. If a specific processor fails or becomes obsolete, the system simply routes the data to a different backend. This chart shows the QKC benchmark doctrine in action. Every execution route must be tested against established classical and hybrid baselines. The system only authorizes deployment when the new computational pathway can explicitly exceed the baseline metric. Raw processing speed is then converted into strict operational KPIs. A faster execution time translates directly into quantifiable, real-world metrics, like reduced supply chain latency or increased power grid efficiency. Insisting on empirical proof for every execution route filters out speculative claims. Strategic infrastructure investments are tied directly to verified performance data. For critical environments, this software architecture is packaged into the A-Enclave sovereign appliance. This is a mathematically bounded, rack-native hardware unit built explicitly for high-security infrastructure installations. The appliance enforces non-negotiable trust boundaries. All external connections require strict route allow listing, and the system maintains absolute role separation between the administrators managing the hardware and the operators running the workloads. Every action passes through the trace engine. This strict subsystem records execution lineage, back-end choices, and configuration changes for institutional auditing. This guarantees that unauthorized experimental pathways cannot bleed into live production routes. Computational speed carries zero strategic value for a national grid or defense network, unless it is paired with absolute compliance and total sovereign control. The final architecture phase activates when proprietary physical quantum processors reach maturity. The new hardware module simply slides and locks into the existing appliance chassis. Because the software layers and governance protocols were engineered specifically for this insertion, the transition requires zero architecture breakage. The audit traces, trust boundaries, and routing policies remain completely uninterrupted. The QKC family solves immediate combinatorial bottlenecks today, while laying down a continuous, governed compute pathway. The infrastructure solving today's routing failures is the exact same infrastructure that will house tomorrow's sovereign quantum processors.